So here's x, x is in blue and y is in red. So that's both of them graphed with respect to the independent variable t. So taken out of that parameterization. Okay. I love how there's a button over here that says go away. Okay. All right. So any questions? So we're going to take a break shortly. I don't know how to write that exception to the rule, but if you flip over to, where is it? 392, theorem 2. So it says, let lambda 1 and 2 be the eigenvalues of the coefficient matrix of the linearized system associated with the almost linear system. So we linearize it, find the eigenvalues. These are the two exceptions. If lambda 1 equals lambda 2 are real eigenvalues, then the critical point 0, 0, that's of the linearized system, because 0, 0 will always be a critical point there. Then the critical point 0, 0 is either a node or a spiral point. You can't determine exactly which one. So there's some, that's what we would call bifurcation. Small errors could send it one way or the other. Okay. So a node or a spiral point is asymptotically stable if lambda, if they're both less than 0, unstable if they're both greater than 0. Now this is the other sensitive case. If the two eigenvalues are pure imaginary, then it's either a center or a spiral, but you're not able to tell exactly. Okay, those are the two sensitive cases. Otherwise, if lambda 1 and lambda 2 are any of those other situations, then the critical point of the almost linear system, the linearized, of the original, is the same type and stability as the critical point 0, 0 of the associated linearized matrix, or linearized system. So they're the same in all those cases, except when the eigenvalues are equal. Okay, regardless of the sign, if the eigenvalues are equal, that's not enough to tell you exactly which type and stability of the original system. Or when they are purely imaginary, 0 plus bi, 0 minus bi, so plus or minus bi. But it's pretty good. It says that it will either be a spiral or a stable center. All right. So let's take a break, and then we're going to do some more, and we're going to do some applications with it.
You know what?
That just blew it out of the water.
We were in
The great frontier
All right.
of Western life.
So one thing we're going to look at this as far as an application is ecological models. So population models, population of two sort of competing species. All right. So say we got two competing species or populations. One is a predator population, and the other is its prey.
Cat and mice.
Right, cat and mice, could be sharks and or whales and shrimp. It could be foxes and rabbits, whatever. Okay. So predator and prey, and these populations are given by x of t and y of t. So the model would be, oh, by the way, x is going to be our prey population, y of t our predator. So a simple model, and this is one just talking about the rates of change. So first derivative, rate of change of each population over time.
It was kind of cool. I watched this special on wolves and elks, and it's interesting how many different variables that come along
Oh, yeah. Yeah, this is going to be fairly simplistic, but yeah.
In Yellowstone, they introduced wolves.
Mhm. Yeah, we have wolves now in Oregon. There's a fairly healthy wolf pack.
Well, there's an interesting to the predator thing too, from foxes and wolves, and how they affect each other, and elk, and then live greenery and stuff like that.
Mhm. There's all sorts of stuff, and they're not only dependent on each other. Of course, there's also usually many other variables. So one thing to note that these two functions usually are nonlinear. Okay, unless it's a very simple model. But this is one actual famous model came about in the 1920s. And that is the Lotka-Volterra equations. Lotka-Volterra.
Sounds like an expensive car.
Yeah, it does. Because Volterra was an Italian mathematician. That's why. Yeah, so it's got that sound to it. So X is the prey population, and Y is the predator population. And the set of equations that actually they came out with them, I guess, independently, or one of them came up with it first, but then someone else unknowingly expanded on it, used it. But dx dt equals ax minus p times the product xy. If you factor an x out of that, you just get a minus py. And that's for positive a and p coefficients. So we're not going to allow a and p to be positive or negative. We're just going to say a and p, all the coefficients here are going to be positive. So a and p both greater than or equal to 0. And dy dt negative by plus qxy. Okay, and in this one, if you factor out a y along with a negative sign, you write it in factored form, negative y, that would be b minus qx. All right, where b and q are both positive. B and q greater than or equal to 0. All right. Why did they choose these? It's not just random, but instead of just explaining with words the assumptions that went into it, show you here. All right, so there's the equation. And we're going to go through these assumptions one at a time and see how they work in the model. Okay, so the assumptions that went into this model. All right, or that you can infer from this model, one way or the other. First, the prey population has an unlimited food source. Okay, and that population, the population of prey, the rabbits or the little fish, the population would increase at a natural rate, and what the natural rate means is according to the law of natural growth. It would increase at a natural rate in the absence of the predator. So you can see in the first equation, that's the prey. You can see in this equation, if there are no predators, you set y equal to 0, look at what you get. A times X, that says that the growth rate of the population is proportional to the existing population. So the larger the population, the larger the growth rate. There's more to multiply, right? And the solution to that would be exponential function. That would be natural growth. It would be exponentially increasing, okay? So that's built into the model. The coefficient in front of that is positive. Now, on the other side, the predator, this is a simple assumption, has no other food source other than the prey, and so they would starve in the absence of prey. Okay. Oh, geez, this should be when x equals 0. It shouldn't. Yeah. Change that. So it should say dy dt. When there is no prey, that's x. When there is no prey, when x is equal to 0, look at what happens. Dy dt equals negative dy. So the population growth rate is negative. It's decreasing at a rate corresponding to how many are present. Okay? So eventually they die out. It would be exponentially decreasing. You get an e to the negative bt in your solution. Right? Initial population times e to the negative bt. So in the absence of prey, the predators would die out. Whereas in the absence of predators, the prey would do very well. Okay, so that explains the difference in the coefficients in that linear term out front. Okay. All right. The third assumption, the rate of predation, it's a fun word, is proportional to the rate of interaction between the two populations. And they build in this interaction term, the xy term. And they talk about it a little bit in the book. If there were twice as many prey in the population, then it would go to figure that there would be twice as many interactions. But if there were twice as many prey and twice as many predators, then there would be 4 times the interactions, potentially. So they build in this xy term, the interaction between the two populations. Now, interactions or meetings, that's going to be good for the predators, right? The more they can find the prey species, the better they're going to do. They're going to have a food source. So the more interactions, better for the predators. The more interactions that there are, not so good for the prey because they're going to lose, right? So look at this. The more interaction there is, this is the predator population. We're adding a QXY. In other words, the more, that's positive, it's going to add to the population rate, positive growth rate. Okay? So interaction would lead to a decline in the prey population, thus a minus PXY, and P would just be some coefficient, right, of the interaction. So it's going to decrease the prey population. Whereas those same interactions will go to increase the predator population, thus you have a plus in front of the XY interaction term. Okay? So they're very similar equations. Very similar, except the signs are opposites. Okay, in each term. All right. So as a specific example, and we're not going to solve this, but if X represents the number of rabbits, and this is measured in hundreds, Y is the number of foxes. If you take those coefficients, then you get this specific system of equations. Okay? And it is not quite linear, but it might be almost linear, right? So we can analyze it. One thing to notice is that 0, 0, since there is an x, well, there's a variable in every term. One thing to note, 0, 0 is a critical point, always. Kind of a boring one, because what does that mean?
Everything's dead.
Right. If at any point, both the foxes, there are no foxes and no rabbits, then it stays that way forever. That would be an equilibrium. Now, whether or not that's stable, I don't know, or unstable, probably unstable. But we're not really interested in the application. We're not interested in x is negative, y is negative. But 0, 0 would be a critical point. Maybe it's an unstable saddle point or something like All right. So let's do an example. All right, so say we got the system dx dt equals 4x minus xy. All right, and if we factor that x out, you could write it as 4 minus y. And dy dt equals negative 16y plus 2xy. And if you factor out that negative y, like they do in the general form, negative y, we have 16 minus 2x. All right, so first let's find the critical points. So let's actually go through this and talk about it by hand. So if we set both of them to 0, first equation would be in factored form. It's nice to keep it that way. 4 minus y, set that equal to 0. And what does that tell us? Solutions to this equation? Or x equals 0, right? We're going to get 0, 0. But 0 and 4. So 4 would be the non-zero critical point just in the first equation. Second equation, we set dy dt equal to 0. Negative y, 16 minus 2x. Set that to 0. And what do we get? Y equals 0 or x equals 8. Now, a critical point of the system is an ordered pair x, y that satisfies both 1 and 2, right?
So,
X equals 0 and 4? Or
Oops. X equals 0, y equals 4. Good call. Okay. So what are the ordered pairs that would satisfy this?
X equals 0, y 4.
Well, if I choose x equals 0, then obviously x can't equal 8 as well. I could get the pair 0, 0.
we could choose 8 and 4.
But if y is 4, then y can't also be 0, but x could be 8. That would also make it. So 1 from here and 1 from here, we could have 8, 4. All right, so we have one non-zero interesting critical point. So I don't want to go about categorizing the 0, 0, 1.
isn't it just that you consider it a trivial solution?
It's kind of trivial. Yeah, 0, 0. Yeah. There's no way that they could ever jumpstart their population back up. Right? Okay. So let's work with, I think we're just going to work with 4, the 8, 4 solution. All right, so let's find the related Jacobian. So Jacobian of these two functions. So this would be my f of xy. This one would be my g of xy. And for this, I'm going to just leave it in unfactored form. But so at a general point xy, Jacobian, partial with respect to x. So take f, partial with respect to x, then y. Take the second one with respect to x, then with respect to y. All right, so what do we get? Partial of f with respect to x, I get 4 minus, right. Oh yeah, in the factored form, you can actually kind of see that. It would be 4 minus y times x. So with respect to x, the coefficient is just 4 minus y. All right, and the partial with respect to y, that term is gone, and I just get minus x. That's the coefficient in front of y, so it's first order, first degree, so I just get the coefficient negative x. So the function g, partial with respect to x, that term goes to 0. This one, it's with respect to x, so it's 2y is just its coefficient. And finally, with respect to y, oh, I'm going to use my factored form. I'm going to get 2x minus 16, I think. Or negative 16 plus 2x. Okay. And we evaluate this at, I'm going to just talk about 8.4, like I said. The Jacobian evaluated at 8.4, and just as a reminder, this is our x naught, that's our y naught. So when I do 4 minus y, it's 4 minus 8, 4 minus 4. We get 0, negative x, opposite of x, so that's going to be negative 8. 2 times y, that's 8. And negative 16 plus 2x, that's 8. Yeah, I get 0. You get 0 on the diagonals. This matrix by itself. Oh, right, okay. So, just to go back to that theorem that talked about when a system is nearly or almost linear, mostly linear. It's like in Princess Bride, mostly dead. This is mostly linear. Because, so what it talked about was, okay, so we have a critical point, we got that. The Jacobian matrix evaluated that at that critical point. Here's the Jacobian. The determinant of that would be 0 minus negative 64. It would be positive 64. The determinant's not 0. So this is an invertible matrix. The original two functions, they're polynomial functions in x and y. So their partials exist and they're continuous. So this is a nearly or almost linear system, whatever they call it. Almost linear, nearly linear. So this does meet those conditions. All right, let's find the eigenvalues of this Jacobian. This is nice. It's just going to be 0 minus lambda, so that's negative lambda, 0 minus lambda on that diagonal, minus negative 64, right? So it's plus 64. Equals 0. So that's lambda squared equals negative 64. So what do we notice? Complex, but in a particular way. Lambda is plus or minus 8. These are purely imaginary. They have a 0 real part. So this is that one case that we talked about. This is a sensitive case when we carry it to the linearization. The small nonlinear part of those functions may what they cause perturbations in the Jacobian matrix that would make it different from the original nonlinear system. So this is a sensitive case because maybe if this is slightly different, if this is positive or negative, it goes from if it really is purely imaginary and it's a linear system, this would be. Pure imaginary, we just get sines and cosines. With the same period, we would have a center, right? And x and y would be going back and forth, but there would be no dampening or magnifying of the amplitude. There would be no e to the pt out front. So small changes, though, maybe this is actually 0.001, and that would put an e to the pt out front, or negative 0.1, and that would make it a spiral. So small changes out here, that nonlinear part could cause changes out here. So if you look at the table on 393, it's either a center, in which case, it's stable. center is what we get if we have a linear system and I get purely imaginary eigenvalues. Okay, but any small error from that linearization could cause a non-zero real part, and that would turn it into either an unstable spiral or a stable spiral, depending on the side. So it's a center or a spiral. And stable or unstable, can't tell yet. So how are we going to determine which one it is? Well, it needs a little further investigation. But, you know, the good thing is we're going to investigate it graphically.
So knowing if this was if we found that this was stable, that would mean this was the equilibrium point that the whole population model is moving towards?
Well, 8,4 is an equilibrium point. The question is it moving towards that or away from it?
That's what
Those
I'm
small
asking, yeah.
differences in that stable or in that critical equilibrium population, with small changes in that, cause the system to go wild?
Yeah.
Or is it going to be small differences from that? Would it actually return back to that equilibrium?
And with our other population model, 0, 0 was always the unstable one, and like the carrying capacity was always the stable one, correct?
Say that again?
The unstable one in the pattern is 0, 0.
Right.
You move slightly above if you want to go up. or away from it.
Right. Yeah, we had those in the single equation
Yeah.
population models. That was the logistic.
So then could you simply try and evaluate it by considering a point that's just barely above and barely below and see how
That's what the linearization is.
Yeah, so the linearization, yeah, we did it near, and we either, center or a spiral. So what we're going to do is just default, and we're going to look at the phase portrait. Phase diagram. Okay. So let's take a look. Let's put this system in there. There we go. So the original equations right here, 4x minus xy. Oops, x times y. And negative 16y plus 2x times y. We'll go to negative 1 to 14 and negative 1 to 8 in the y direction. Okay. So here'd be just the direction field alone. Phase portrait also includes some actual trajectories. And what does it look like 8,4 represents?
An egg.
This would be a
Is this a chicken and like fox or something?
It's a chicken population.
foxes and rabbits. They like to do that. So X, remember X was the prey population. So it looks like, and time is sort of distilled out of this. Y represents the population of the predators, so foxes and rabbits. So it looks like they're going back and forth. They're varying with respect to each other, but in a periodic way. So these are closed. And this is, what kind of critical point was this called? Center. Yeah, and it's always stable. A center is stable. It returns. It's a closed.
So whatever point you start at, it'll be cyclical in that orbit around that center.
Mm-hmm.
0, 0 would be a sink.
I don't know.
This is what is it? Asymptotically not stable or something?
Zero is a little bit different.
Is it saddle point?
So y is, if there's a ton of, that's a large y values, very small x values. This is what happens when there's a large number of predators out there,
Will that be bigger?
foxes, but very small number of prey. The population drops dramatically, and when that happens, the fox population is near zero, and the rabbit population explodes.
But that'll eventually come back up all the way around, like in a circular
Well,
motion.
Can we see
Yes.
X and
Yeah.
Y?
Have to.
Can we see X and Y with respect to T?
Oh, yeah.
Yeah, good thing.
Yeah, good thing, but all the way on the outside.
All right, so let's take a look at this with both X, Y, and T, and you can choose, all you do is click on it. So one like this, if it's very close to this critical point, look what happens. So X is the prey.
They're just slightly off.
Just go back and forth, but yeah, they're out of sync a little bit, right? When the rabbit population is at its greatest, the fox population is increasing.
It's basically sine cosine.
Yeah, they're
Wait,
sine
wait, wait.
cosine.
Yeah.
Same
Sine
period.
cosine.
Catching up.
The slope of one is the slope of the other. It's weird. Because when rabbit population is its highest, that's when fox population is increasing the most.
Mhm. But yeah, even when the population starts going down, that's still increasing for a while. So they're out of phase with each other.
Yeah.
Yeah. All right, and they don't in this particular trajectory, the populations are totally they don't overlap. You can see that over here. The population of rabbits is between like say 7 and 9, whether that's hundreds or thousands, whatever. The fox population is between 3 and 5.
Oh, couldn't you look on the graph?
Yeah, but yeah, you can tell by looking at this as well. So X only goes between 5 and 7, whereas Y goes between 3 and some change and almost 5.
What happens if you click it so it shows it in 3D?
I don't know.
Let's
I
try it.
tried to, but another. If you can click on another one and get a different graph. This trajectory, the populations actually kind of overlap at certain times. But yeah,
So
when
if you go further out, then they overlap more.
Yeah, go to one that was this close to 0.
Asymptotic,
Yeah.
and an asymptotic one.
you can keep going, yeah, and there we